Okay, my friends, so I realized as I was getting ready to record this video, I probably should have started the day with this video, considering the topic. It really doesn't matter. You're going to learn the same math, regardless of the order. But the reason I should have started with this one is, we're going to show you in this video how to calculate the sample size necessary for a study. So if you think about it, you kind of have to know this number before you even start the study, because the study is dependent on how many folks or how many things you survey. So whatever, we'll do it now instead. So here's the deal. We're going to do a sample size calculation. Sample size calculation. Now here's the deal. Calculation. This only works for proportions. This is going to be based on a percentage study, not for an average, not for anything else, just proportions. So sample size calculation for studying a proportion P. And you're trying to get a P hat that studies that proportion P. Okay. It's actually based on the future margin of error you will get from the study. Now check this out. Check this out. The margin of error formula that we learned in the last series of videos is equal to your confidence multiplier times the square root of P hat times 1 minus P hat all over the sample size n. Now if you look at that equation has an n in it. Boop, right there. All we got to do is solve this equation for n, and then talk about the remainder of what we get. So we're going to do is a little bit of algebra here. If you don't like algebra, just like maybe you didn't like it in that last video from the last playlist, you can just fast forward this until I've got n on one side and everything else on the other. So I'm going to have some fun with algebra here. So what I'm going to do is I'm going to go ahead and I'm going to divide both sides by that z first. And that's going to take, we're going to have the margin of error then over z. And that's going to equal the square root of all this mess. N. Okay, now I'm going to square both sides to get rid of that square root. That's going to be margin of error over z squared equals p hat 1 minus p hat all over n. Okay, real quick, I'm out of board. Let me grab my eraser. Make sure I'm up top. I'm going to bring this up there. I don't know about you, it's kind of pissing me off that the n is in the denominator over there. But since this whole thing is just a proportion, I'm going to take, these are both fractions, right? This is a fraction. I'm going to take them and just flip them both, because they would be equal to each other that way. So I'm going to have, and I'm also going to square each of these pieces. So you got z squared, margin of error squared, equals n over that. P hat 1 minus P hat. Okay, we're almost done. All we got to do is move this, which is just a number, over to this side. So you're going to end up with z squared times P hat times 1 minus P hat over the margin of error squared equals the sample size. Cool. I'd like to tell you that all you've got to do is plug numbers into this, and that'll tell you what your sample size needs to be. But I can tell what some of you are thinking. How the hell can you plug a P hat in when the P hat is what you get from the study, but you're trying to figure out the sample size that you need for the study? That's like a chicken-egg argument, right? And you're absolutely correct. You are absolutely correct. So the way I deal with this, I think the way most statisticians deal with this is they say, you're not going to know what P hat is yet. So what you're going to do is, you're going to assume that the value of P hat is such that it makes the sample size as large as possible to minimize error. Now, if you tried the extra credit problem from the previous homework, you actually addressed this. And you found out that, and I'm happy to explain this more if you want to shoot me an email or drop in for a Zoom meeting. This product, P hat times 1 minus P hat, is always going to be a decimal. So for example, if P hat is 0.3, then 1 minus P hat is going to be 0.7. So let's just make a little table here. You can see what I'm talking about here maybe. 1 minus P hat Okay, so if p hat is, let's start with 0.1, maybe 0.3, 0.4, 0.5, and then see what happens if we go past 0.5, maybe 0.6. These are all probabilities that we could get from the study. That means 1 minus p hat is going to be whatever's left. So that's 90%, 70%, 60%, 50%, 40%. The product of those two things is what is going on right here. So this is p hat times 1 minus p hat. So 0.1 times 0.9 is 0.09. 0.3 times 0.7 is 0.21. 0.4 times 0.6 is 0.24. 0.5 times 0.5 is 0.25. 0.6 times 0.4 is 0.24 again. And if this keeps getting bigger, this keeps getting smaller, and this product is going to keep getting smaller. As a matter of fact, the largest value that this could ever have is 0.5 if p hat is exactly equal to a half. Because I just misspoke. The largest value this can have is 0.25, because if p hat is 0.5 and 1 minus p hat is 0.5, then together they multiply to make a 0.25. So what statisticians should do, and what I always do when I'm calculating a minimum sample size is, I just say, well, worst case scenario is these two things are both going to be equal to 0.5, which means you're going to have 0.25 up top times, I'll just put it in parentheses, times z squared. Okay. Now this is looking better. Believe it or not, this is looking better. Because here's the deal. You can pick these two things before going into your study. Z is the value you pick based on what confidence you want. So suppose you want 95% confidence. Then you will plug in 1.96 for Z. Suppose you want 99% confidence. I can't believe I said that out loud. I think that would be 2.58. I think. I'm going by memory here. I can't remember. Whatever confidence you want, it's got a Z multiplier that you can plug in there. Boom! And you can also decide, how off do I want to be? How large a margin of error can I accept? Change that to a decimal, say it's 3%, and plug in 0.03 right here. 0.03 becomes your margin of error. Take that, square it, square that, plug in the 0.25, and that's going to tell you your sample size. Let me show you some examples on the computer, and also I'll show you the last tab in the Excel calculator for this lesson that actually does all this for you, because there's a lot of places that things can go wrong in that calculation. So I'll run a couple for you online, and then you can get it to homework. Okay, my friends, so I'm going to use my favorite calculator, Google, and we'll do a couple examples here, and then I'll crack open Excel calculator and you can see what's going on. So the first example, I'm going to write down what I'm going to do here so I remember it when I get to the Excel calculator. This first one, let's assume we're going to run a 95% confidence interval, and we want no more than a 3% margin of error in our study. Okay, so the formula says 0.25 times, if I'm going at 95% confidence, that's 1.96 squared. That's the numerator of the fraction, and if you want, you can put it in parentheses, although you don't need to. Oops. And then we're going to divide that by the margin of error squared. Now, the margin of error is 3%, which is a decimal is 0.03. You got to have the 100 accounted for somewhere in there. So we're going to square that. And this tells us if we want to have 95% confidence and no more than a 3% margin of error in our study, we better have at least 1,068 people. I'm going to round this up always just because rounding down means you're sacrificing either too large a margin or a larger margin or less confidence. So 10,000 or 1,068 is going to be your sample size for this one. Okay? So there's one example, and I'll show you how to do that in the calculator in a second. Let's just change it to something else. Let's do 99% confidence, but let's accept maybe a larger margin. So let's do a 5% margin of error. Okay? So same calculation we just did. I'll just leave it in this window. That 0.25 is still going to be there. For 99% confidence, it's a 2.58 rounded off. It's actually different than that, but 2.58 is rounded. And then a 0.05 margin, and you can see you only need a 666, I love that, 666, a sample size of 666. I totally made those numbers up. I had no idea. Okay. Now you can also see the effect of a smaller margin. Suppose, actually, you know what? Let's do this in the Excel calculator. We'll play around the Excel calculator next. Okay, my friends, so now we're in the Excel calculator. Yesterday we played around with the confidence interval for one proportion tab. We're going to now go to the next tab over, which is sample size for one proportion. All right, I'm going to zoom in a little bit so we can see better. Let's get in there. There we go. Okay, so all you got to do is plug in your decimal version of your margin of error and your confidence, and you can tell it with the confidence. You don't have to look up the z-score. I've programmed the spreadsheet to actually look up the z-score for you. As a matter of fact, the first two in here, 3% maximum margin of error and 95% confidence, that's the 1068 we got online. So it already has the formula. It's up here if you're interested. That's what it looks like as far as the math. If you're interested, you don't have to be interested at all. What if you will accept a 5% margin and you want 99% confidence? There's your 6.6. Look at this, 664. And the reason it's different here versus the one we did is 99% confidence is not exactly a z-score of 2.58. It's actually a z-score of something like 2.576 and then a bunch of other decimals. So this calculator is using this norms inv command, so it's using more precision. So 664 will do it. What's cool is with this calculator, you can actually then change. Okay, so suppose we didn't want as wide a margin of error. Suppose we only want a 4% margin of error. Well, your sample size just went up now, didn't it? Suppose you want a 0.03 margin. Well, your sample size went up again. Suppose you only want a 1% margin. Well, it's so big now that we have to extend out the column to see it. You need a 16,588 minimum sample. So the margin, and that mathematically that makes sense because you're making the denominator of that fraction smaller and smaller and smaller, which makes the fraction value itself larger and larger and larger. Okay, my friends, I think you got everything you need to crack open day 12's homework. Go get them.